a couple of things. Can you hear me okay? Can you see my screen, which should come up in just a bit? And are you ready to get started? Wonderful. So today, first of all, since today is our last lesson together with me, not your last lesson, but our last lesson together, two things. This is the background. No, not the back. I actually wanted to invite you to connect with me. I left my contact details on the network channel. And today we're going to talk about something that is very, very, very interesting and important to me, which is data science. After all, I am a data scientist. And there is a little bit of a difference. There's places where they mix, but there are some difference between data analytics and data science. But I do want to let everyone that wants to go into data science, that's very interested in machine learning and artificial intelligence and wants to go deeper, you already took the first steps because you're already working with data analytics. So a few steps forward and you will go into data science as well. So today we're going to be talking about the differences between data science and data analytics. We're also going to be talking a little bit and giving you an introduction on machine learning. In other words, what is this thing we call machine learning? What are some of the algorithms that are used, some of the tools that we use, and what we use it for? We are also going to talk specifically about the machine learning lifecycle, because this is what most of data science is. We pick a project and we start working with data towards building a machine learning model. And finally, we're going to go through a very, very high-level overview of supervised learning and unsupervised machine learning. You'll see more about these on Thursday, which on your optional lecture. Great. So what exactly is it when we talk about data science? A few years back, probably about 15 years ago, maybe a little bit more, and a new bunch of careers started popping up. These were not your regular careers where people hyper specialized on something, but it was something a little bit different. It was something where people were grabbing bits and pieces from different places and putting them together into one big career path, which was something that we didn't used to do before. We used to do hyper specialization. Data science is one of these new career paths. And what it does is that it takes a little bit from different places. So for example, it uses a scientific method, it uses algorithms, it uses systems, it requires a lot of domain expertise on whatever it is specific that you're working on. So for example, if you're working on building machine learning models for folding proteins or for social media marketing, you need to understand that part of the business, that part of the industry before you apply what you know. And then we use programming, maths, statistics, and what we know about algorithms to put everything together into building this initial piece of artificial intelligence, which we called machine learning or a machine learning model. And the insights that come out of these models are used to predict the future, to predict what could come, and to even create prescriptive analytics. In other words, to tell the system what to do in case something is predicted one way or the other. So what are the difference? Because you've been working with data as data analysts, data scientists work with data. So what are specifically the differences? So I want you to think about it like this. Because there are some key differences, but you're also going to find a lot of things in common. So in data analytics, you process is the whole process that starts with collecting data. Then we clean the data. Then we transform the data. And with those transformations, we start extracting insights. So we do use statistical methods, a lot of visualization techniques that allow us to understand, is the trend going up? Is the trend going down? What's happening? What's happening with this group of customers? What's happening with the other group of customers? So those are the kinds of things we do in data analytics. And once we pull out these insights, whatever it is that's happening, we communicate them. We find a nice way to show people through great visuals through great storytelling what's actually happened. Now, data science is a little bit broader than that, because we actually do, in data science, you do everything that you do in data analytics and then some. Now, so it encompasses all of data analytics, but it also adds things like machine learning. It adds artificial intelligence, some software engineering, and we're going to use all of these tools and techniques to build predictive models. So in other words, it's not just descriptive and diagnostic analytics, but now we move into the world of prediction. We're trying to predict what's happening in the future according to the data that we have. So that allows us to develop new algorithms, and that helps us build and solve newer and more complex problems. So I want you to think about it like this. While analysts are generally much more focused in understanding the past and the present, which is descriptive and diagnostic, data scientists are more focused on predicting the future, which is predictive and prescriptive analytics. So trying to figure out what's going to happen and what should we do, trying to automate it. If it happens, if something happens this way, we do this. If something happens the other way, we do something else. Now, oh, by the way, do feel free to ask any questions whenever they pop up at any point. Today's a great day for questions. So if we're thinking about data science, we're actually thinking about the whole world of artificial intelligence, machine learning, and deep learning. So whenever you use all of these words, they sort of all mean the same thing. We're building some kind of machine learning model. There's a big joke out there that says that at the end of the day, we started with statistics, then we started calling it machine learning, and now we're calling it artificial intelligence. But at the end of the day, it's statistics, actually statistics and probability, with a lot of algorithms and programming. That's and computing power, of course. All right. So let's think about it. Probably this way is the best way to think about it. So we have all of this world, which is data science. And inside data science, you can find data analytics. Now, on the other side, we have all of these, which is AI, machine learning, and deep learning. So AI is a general field. It's a big field that has everything to do with how do machines think? Can machines do things similarly to the way that people do things? That is artificial intelligence. Now, inside artificial intelligence, there's this big area called machine learning. So most artificial intelligence as we know it today is machine learning based. In other words, it's some kind of machine learning that is actually doing it. There are others. There's a whole other field called semantic artificial intelligence, which has other things, and it hasn't developed as far as machine learning because machine learning is actually giving us so many good results so quickly. And so that's another one. And finally, there's deep learning. So deep learning is a very particular way of doing machine learning that uses much more complex systems. So instead of just using one algorithm, one model to actually run the data and create predictions, we actually use things called artificial neural networks. So it's trying to figure out, so imagine trying to figure out each node is like a neuron that has a little bit of a different algorithm than the other ones. And then everything runs through many layers until it starts figuring it out how all these data is connected. That would be deep learning. And data science and deep learning, and everything, they're connected, but not all artificial intelligence is data science. Just like not everything that has to do with artificial intelligence is done by data scientists. So a question, data scientists focus on making predictions. Yes, in my experience, how accurate are those predictions, roughly speaking? So that is a huge part of what we could talk about. So here's a few things. First of all, accuracy is going to depend on what we're trying to do. And generally, it's not a matter of trying to get 100% accuracy. It's trying to be better than whatever the common or existing method is. So I want you to think about it like this. If a doctor can diagnose any kind of malady or disease with a 90% certainty, If we can build a machine learning model that can do it with 92% certainty, we're better off. That's all it means. So we do need a baseline. So again, it's not a matter of getting to 100%. So that's one. The second one is it's not always, accuracy is not necessarily the best thing. There's other metrics that we use that is not exactly accuracy, because at the end of the day, predicting what's happening in the future is very difficult. But we have been able to build models that are very good. So for example, going back to the idea of diagnostics, there are diagnostic medical models that are 93, 94, 95% accurate, which is very, very, very good. Like they can actually, they can be better in some cases than a group of doctors working together. So imagine, these are very powerful models and they are much easier to scale. So that's the other thing why we want to use them. What can go wrong? And when it does go wrong, how can we fix it? There's so many things that can go wrong. So, but that would be like a whole seminar about what can go wrong in machine learning, and it would actually take a few weeks. But if we have time at the end, I will talk a little bit more about that, because that's really interesting, actually. Yes, so accuracy, precision, recall, there's F1, there's different metrics that we use, not just accuracy, depending on what we want to achieve and what the idea of the model is. Remember, what we're trying to do is not predict the future with perfect certainty. We're trying to build models of reality that are better than what we have right now. So imagine anything that is better at predicting or gets closer to whatever prediction we can make as humans today with whatever mathematical model we're using. If we can build a model that can exceed those expectations, we are better off, and we can just keep working on it until it gets refined better and better. Yes, there is a whole area in machine learning. It's starting with that has to do with what can go wrong, and it has to do with data governance, data ethics, and I forgot the other one. But yeah, there's whole areas opening up nowadays, especially with AI becoming so big and interesting. So here's a first question just about what we've been talking about so far, just to interact a little bit more. Which of the following best describes the relationship between data science and artificial intelligence, machine learning, and deep learning? So is data science interconnects with AI, ML, and DL? Is data science a subset of AI, ML, and DL? There is no significant relationship, or they're all subsets of data science? Yeah, great. Exactly. Data science interconnects with AI, ML, and deep learning, because I want you to remember that there's a ton of other professions that are working on these areas. So everything from computer scientists, data computer engineers, we've got data science, and we have data engineering, not the same career, although it crosses over with many things. We have a lot of people just working in ethics, working in modeling, working in algorithms, working in mathematical modeling that have something to do with artificial intelligence. So there is a lot going on. And here's another question. So data science would involve which of the following processes? Data collection and cleaning, data analysis and visualization, or building machine learning models? Pick all that you think that are included. So great work. Yes, all three. If you remember, data analytics is a subset of data science. So everything that data analysts do, data scientists should know how to do. So that means that data collection and cleaning and data analysis and visualization, which are part of data analytics, are also part of data science. And of course, building machine learning models is also part of data science. Yeah. So here's an interesting question before we move forward. You've probably heard or used something called ChatGPT, right? Right. So See, that's a good question. Where do you think, let me actually move back a bit. Where do you think in here does, just in this part of artificial intelligence, machine learning, and deep learning, where do you think that ChatGPT falls? So it definitely falls under artificial intelligence. Yes, that is a given. So here's an interesting thing. So ChatGPT and all of these large language models are deep learning models. They're all deep learning models, but not all, but they also use some other interesting things. So I would actually put it like somewhere around here. And over here, there is a big field called natural language processing, or NLP, which is the way we process natural language. That's why we can actually chat with a system like ChatGPT, and it's actually fairly decent at keeping up a chat, or at least it's fairly decent at imitating what we do. I still would not call it that reasoning, but that is another big debate. All right. So remember, everything that has to do with deep learning is also part of machine learning. So deep learning is a subset of machine learning. Very important. And both of them are subsets of artificial intelligence. So as we talked, data science encompasses many, many fields. And using machine learning as the core component. So let's talk about this machine learning, because it's true. I would say that 90+% of all projects led by data scientists are some kind of machine learning process. So let's talk about exactly what this is. So how does machine learning actually enable us to make better decisions? Or because that's the whole idea. So I want you to think about machine learning as a function. So it can be a function in Python or a mathematical function, whichever you prefer. They both work at the end of the day. So imagine that what it does is map all of the input variables, so all of the data we put into it, and it maps it to an output variable. Because remember, what we're doing here is we're adding a lot of information. Okay, so here are, for example, these are the age, or these are the heights of this amount of people. And we're telling it that for each pair, or each height, there's also a weight. So how much that person weigh. So height and weight. So we have those pairs, we feed everything into the system, and the system, the algorithm, should actually figure out what the relationship is between these. So is there a relationship between height and weight? It should find it. In this case, there is. It's sort of linear, so it does find a formula for it. Once we actually find whatever relation there is, so imagine that this eventually becomes a formula, which some kind of formula, where, again, mathematical formula, which we also call weights, not to be confused with the weight of a person. Then we can actually use that formula into the machine learning system or model. We input new features that it's never seen before, so a new set of heights, and it should use this formula to predict a set of weights. All right. Let's do another interesting one. So imagine that you feed it, we're teaching it to recognize pictures of dogs. So we feed it a lot of pictures: dog, cat, dog, etc. So a lot of pictures of dogs and cats. These ones, some of them say dog, the other ones say not dog. That's it. It's just one or the other. And what it comes up is one kind of formula or something, what the relationship is between the pixels in the image and which ones are dogs and which ones are cats. So once it has this formula, we can just plug it into the system. We feed it a new photo, if it's a dog, and we expected it to say it's a dog. If we feed it a picture of a cat, it goes to the formula and we expect it to say not a dog. That's it. So at the end of the day, that is the whole idea. So we just want the machine to learn the patterns to learn the relations, to create a formula to actually figure out what those relations are, and then we can use it to predict something. Yes, so sort of like when we were sorting things with SQL, we can actually sort things with machine learning. But remember, the difference is you sorted things in SQL that had labels. We want to train the system with labels, but then we want to use the system without labels because we want to feed it new images and the system has to figure out what they are. So the difference between a machine learning algorithm and a machine learning model, this one can be a little bit confusing. So when we're building this, when we're creating the relationship, we use a machine learning algorithm. So in other words, there's some kind of a system, some kind of a mathematical model that we use. So here, this is called, for example, there's linear regression, there's decision trees, there's vector support SVM or support vector machines. So there's a lot of algorithms that we use to figure out what this relationship is. So that's a machine learning algorithm. Once this runs and we have our answer here or formula here that tells us how these two things are related, then we build a machine learning model. So again, this is an algorithm, the one that we use here. This is a model. Then we plug this model in here, and then we input new things, and we get a prediction. All right, that's it. That's like the basics of how machine learning works and the big difference between algorithms and models. The algorithm is something that already exists, some kind of a mathematical model, mathematical formula, mathematical algorithm that we use to map out the relationships. Once they're mapped out, that formula that comes out of that system, we plug it into a machine learning model. So that's why we train machine learning models using machine learning algorithms. That would be probably the best way to set it up. All right. So since we're talking about machine learning in general, let's talk about how the life cycle of it works. So we actually have 8 steps. This can change. There's systems that have less steps. There's models that have more steps. But in general, we actually go through all of these. The first one is understanding the business. So you need to understand whatever business you're trying to build something for. So for example, if you're trying to figure out some working on the pharmaceutical industry, you should know about the pharmaceutical industry. If you're working about energy, oil, wind, gas, you should know about the business, because the more you understand the business, the better you're going to understand the data. If you understand the business, then we start with the data mining. So data mining just means, where am I getting the data from? And we're going to see in a bit that there's tons of different places. It can be inside, it can be outside, etc. But there's tons of places where we can get data. Then we move on to data cleaning. So after we got the data, and this you already know, once you have the data, you have to clean it, make sure that it's ready, and we need to prepare it. Then we explore it. So this is we explore the data in what's called exploratory data analysis, because we need to figure out what we can and what we cannot do with it. Once we figure out what we can do, we prepare it. First, we do data splitting. In other words, we split the data into into training and testing, which we'll see in just a bit. And then we do something called feature engineering. We figure out what parts of the original data that we have, we can actually, we should feed the model. And there's tons of reasons why we want to pick more or less features and which features we pick. Then we do the predictive modeling. So this is when we start trying to figure, again, predictive modeling. We run the algorithm through the data, or the data through the algorithm, to try and figure out what the relationship is. And so once we do that, we actually also do some data visualization, actually a lot, to see what the results are, to see what we got. We also do a lot of visualization over here in step 4. But at the end of the day, we're trying to figure out how our machine learning model is actually doing and how we can make it better. So a couple of questions before we go deep into each of these. Machine learning algorithm is like the recipe and the model is the final dish. So that's interesting. So I would say like the machine learning algorithm is the different ways to prepare something, not just the recipe, but because you can actually tweak and mess around with the recipe quite a bit. So I would say that the machine learning algorithm is like the tools. You have your skillet, your oven, your fire, your knives. And depending which set of knives or which, if you're going to use the oven or the skillet, that would be your ML algorithm. And then your model is whatever recipe you're trying to create, because you're trying to create a recipe that you can do over and over and over again. So again, I would say that the algorithms are like the tools of the chef and the models are the recipes. All right. So again, go back to business understanding. Step one. So the first thing is we need to understand what the business is all about. So not just the business itself, but who are the business sponsors? What are the requirements? So what are we trying to build? Why are we trying to build it? And what is the expected outcome? Yes, Bethany.
Just the second ASL interpreter here, just ready to be spotlit and added to the ASL room.
There you go.
Thank you.
Adding you now.
All right, great. All right, so as I was saying, the first part is understanding the business. What are we trying to build? So for example, it's not going to be the same if they ask you, hey, I want to build a machine learning algorithm to predict the price of the stock market, versus if they want to build an algorithm to predict how many clients are going to leave us next month. So again, what's the business? What's happening? What are we trying to figure out? So what is the problem that we're trying to solve? That is the first part. And believe me, it's the most important part. Because if we don't actually understand exactly why or what the problem is, it's going to be very, very difficult to figure out the rest of the problem. So the second part, again, is the data mining or data collection. We need to figure out where we are going to get the data from. Okay, that becomes really, really important. So there's tons of places where we can get the data. The first one, and the one we hope we get the data from, is internal sources. So that's the first. So imagine everything we've done in this course, you have had the data. That means that the data came from internal sources. It was already inside the company before you started using it. And that's probably one of the best places. Data that you can find, transactional data, how much you sold, how much you purchased, which clients bought what. So all of the data from every single transaction, those are the kinds of data that we want to see. If you're talking about an airline, so passengers, roosters, flights, airplanes, that's all transactional data. Master data, this is the data that doesn't move. So it's not transactional. It moves a little bit less. So for example, who are our customers? Who are our employees? So all of the information about the people, the things, the companies that we work with or work for, all of that is part of what's called master data. And then we have sensor data. So if we're working with machines, if we're working, for example, on trying to figure out diagnostics for someone, like imagine a Fitbit or an Apple Watch, those all have sensors, and that data gets recorded, and all of that data we can actually use. And all of these comes from internal sources. So that's the first one. Second, external data sources. So it turns out, for whatever reason, we want to do a project, we don't have the data, so we need to get it from somewhere else. So the first place, public data sets. So again, this is data that everybody has. It's freely and publicly available. Think about Kaggle data sets, think about open source data sets like the US Census Bureau or the European Union Data Center or the OECD, the World Economic Forum. They all have free and open data. GitHub, another great place to get some data sets. Now, let's say that you want, for example, to understand your customers, but there's no data about how they feel about your product. So you start creating something new. So we create something where we can get data. So imagine surveys, whether phone, in person, online, all of that becomes data. And finally, we have web scraping. So any data that's out there on the internet, it's up for grabs. So let's say that you wanted to figure out what people think about McDonald's. So you could go into Twitter, you could go into Facebook, you could go into LinkedIn. You can scrape it for every single post that says something about McDonald's, and then you have your data to build your model. All right. So web scraping, everything that's out there. By the way, this is most of what they did when they built ChatGPT and most large language models. They scrape the web, mostly Wikipedia and tons of other places to get the data. So yeah, there's a lot of data out there. All right, so that makes it to step 2. And we move to step 3, which we love and we need to spend a lot of time on it, which is data cleaning or also data curation. So from all the data that we collected, all the data that we have, we need to, first of all, figure out which one is good for us, which one does not make any sense, and we need to start cleaning it. So again, imagine if you were actually doing a recipe, you want to bake a cake. You actually need to figure out, am I missing any ingredients? Do I have to replace one ingredient with another? How is that going to affect it? Are there any incorrect measurements? So if you get something that happens to me all the time is that I get information from the US. I work on the metric system. So, I get gallons and miles, and I need to convert them because in my head, I understand kilometers and I understand liters. So we need to make sure that we're using the same measurements and that we understand them. That's very important. So that's the thing with data cleaning. We need to make sure that we're using the right metrics, that we know specifically what the data is saying, and we need to make sure that we have the right data. Now, even if we have the right data, there's other cleaning that we need to do. And some you've already very used to. Removing rows with null values. So do we have null values? Do we need to remove them? Do they tell us something valuable? Do I remove them or do I do something else with them? If there are any unused columns, oh, look, there's 10 columns that they never used. Remove them because they're just, getting very heavy and very problematic. Duplicate values. Do we have any duplicates? Should we remove them? Yes, always remove duplicate values. If there's missing values, completely missing values, and we don't want to remove them for whatever reason, what do we do with them? Do we fill them? And if we do we use the mean, the median, the mode, or do we use 0? So again, it's going to depend on the context. And finally, and something that happens a lot, is we need to fix data types. So sometimes you're going to get the data. For example, it's a number, it's supposed to be an integer, but it comes as a string. Same thing. You have a lot of data that maybe it has a little thing at the front or at the bottom or somewhere, and you need to just clean it. It has a space, so it transformed the number into a string. We need to transform it back into a number so we can do things with it. Chris, that's a great question. So if you're going to build a machine learning model, and this is important, if you start with Excel, you can hide them, but then when we move the information into Python, because you're going to need Python, you want to actually get rid of all those hidden rows or columns. You don't want to hide them. You actually want to remove them because if they are in the data, the algorithm is going to pick them up, even if you can't see them. So that's sort of important. All right, so a few issues that happen, just an idea: incorrect data types, numeric variables stored as strings, or inconsistent data types. This one's a little bit more tricky, but it does happen. So we have the same variable in different data types. So sometimes it's a string, sometimes it's an integer, sometimes it's a float, and we just need to pick one at the end of the day. So it's a number, either integers or floats, depending on what you're doing, but we need to pick one and only use one. And that's going to be very important. So every column should only have one data type. So so we know what the problem is, we gathered the data, we cleaned the data. Now comes the fun part. We get to explore it. We do EDA, exploratory data analysis. And I'm just going to go back to a question. Which phase in the machine learning lifecycle do you think is the most challenging? So in my experience, this one. So why is data cleaning the most challenging one? Because it is. Well, first of all, because most data scientists don't like to do it. That's just the truth. It takes a long time. You have to be very careful. I love this part because it helps me understand the data and how it got collected a lot better. But a lot of people hate it. And the thing is that this part is not as exciting as data exploration. So what happens is we want to dive into data exploration like very, very quickly. And I've seen too many cases where people do not do data cleaning as optimally as they should. So that for me, I would say that this is the most challenging one. And again, challenging, not because it's difficult, but because most people don't like this part. I find it fascinating, but in my experience, it's like nobody wants to clean the data. Everybody wants to explore and start building models right away. So yeah, I can completely understand. It's a love-hate relationship when it comes to data cleaning. But if you fall in love with it, you will be in the top, not very high percentage of people that love data cleaning, and they will love you for it, by the way. Wow, Nicolas, that's a great question. Where does ETL or extract transform load? It's not in here. So remember, ETL is something that should happen on your database. So whoever built the database, the ETL process should have been done there so that when you as a data scientist access the database, you don't have to worry about cleaning. You still have some cleaning to do, but it's going to be a lot less. So remember, we just try to figure things out. But again, a lot of the time you have to make sure that the data is clean because it's not necessarily clean. There might be some issues. It might be old. And again, believe me, about 80% of the data I've been sent for projects was not in a database. It was in Excel. We had to create the databases. We had to do other things, or it was built in a very old database model with no normalization, and it has a lot of mistakes. So that happens. But good ETL should happen on a database level. All right. So jumping in data exploration, which is very important. This is the place we're going to understand the statistical properties of the data set. So we're going to understand the shape. So, for example, we're going to get our data set and we're going to see if it's normally distributed. Not the whole data set, but specific variables, specific features. So for example, if, let's say we're looking at client purchases. So are the client purchases normally distributed? Which means, oh, look, there's a mean here and the mode is also in the same place at around, let's say, $100. So that's great. About, it's normally distributed. Great. That's always a good sign. Is it skewed? So for example, do we have a lot of customers and then a few of them that purchase a lot? So we're going to get a right skew, remember? So we're going to get our mean over here and our median over here. Is it left skewed for some reason? Do we have a few people that purchase very little versus most of our clients purchasing a lot more? So all of that becomes really important to understand the shape and the distribution because it's going to allow us to understand our data better and what we can do with it. Then we can check for statistical properties, the minimum value, maximums, mean, median, mode, anything we want, interquartile range, tons of things. And then we start doing a lot of plots. Why? Because we want to see a lot of things in our data. So, what's happening with the data, not just the distribution. We can look at bar plots to see what are the different groups. We can look at pie charts to see the different groups in a ratio manner as well. And most importantly here, by the way, my favorite plot, don't know if you've seen it before, is the correlation heat map. So we run correlations and we use a heat map. And that heat map. So that comes up to something like this, where we have all of the features 1, 2, 3, 4, et cetera, and 1, 2, 3, 4, et cetera, and each square tells us how much these two variables are correlated with each other. And that helps us understand a lot of what can hold predictive value for something else. Because, for example, here's an interesting question. Which do you think has a better predictive value on the price of a house? The number of bedrooms or the number of bathrooms? And I'm going to be very specific, in the US. So again, the question, which one do you think has a better predictive value for the price of a house? Number of bedrooms or number of bathrooms? So it turns out that they're both important, but bathrooms is more important than bedrooms. And this is something very unique that they found the first time they ran the algorithm. They ran a machine learning model to try and predict prices. It turns out that when they were analyzing it, so for example, number of bedrooms is important, but the number of bathrooms is a tiny bit more important. So in other words, a house with 2 bedrooms and 2 bathrooms is much more valuable than a house with 3 bedrooms and 1 bathroom, which is interesting. But at least that's how people see the value of places. All right, so once we do our data cleaning, well, before that, questions about the 4 parts that we've gone so far? So we've done business understanding, mining, data cleaning, and data exploration. Oh, and by the way, before I forget, in data exploration as well, this is where we start figuring out exactly what we want to do. So we're going to decide, oh, look, we might use this algorithm or the other algorithm. Let's start with this one and figure this one out. Because at the end of the day, inside a data set, whenever you have, imagine that you have a table. So let's say you have a table over here and you have all of these variables, all of these columns. One of these columns is going to be your target, just one of them. So for example, price, number of customers. So one of these columns, only one of those columns, not all of them. Because if it's all of them, it becomes really complicated. So using the map, the heat map, can we decide the features that we need for predictions? Well, yes and no. We can figure out which ones are have the highest correlation value, and we can tend to use them for prediction. Remember, and this is important, correlation does not mean causation. I mean, that 2 things are correlated, that does not mean that one causes the other. But if 2 things are correlated, we can use one of those to predict the other, which is not necessarily, doesn't have to do with time, with one happening before the other one. Yeah, so there's tons of tools in data exploration, and you learn more. So for example, some of my favorite ones are violin plots. I love violin plots. I love pair plots, where you see all of the different variables related to one another in a scatter plot, one for each pair of variables. But again, it depends on the data that you're looking at. You might actually use all kinds of visuals. Like if you were doing, for example, protein folding or genomic sequencing, you have tons of other kinds of visuals that you would be using there, which are fun and interesting. But yeah, so that's why I say that the data cleaning is the most challenging part, because everybody wants to jump into data exploration because it's exciting. Data exploration is really, really exciting. So once we do data exploration, now it's time to start organizing our data so that we can actually run our model. And the first thing we want to do is we want to do data splitting. We want to take our data and we want to split it in 2. So, for example, we want to take about 70, maybe 80% of our data, depending on how much data we have, and we set that as our training set. What does the training set mean? This is what the computer is going to be trained on. The computer is going to see this, and it's going to see all of this. So both all of the features plus or target variable. So target variable is what we're trying to predict. So in this case, it's going to see all the features and the target variable. Boom, 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 boom. And this is a 2. Boom, 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 boom. Whatever. So it's going to see everything. This is how it learns how to map this, the target variable and the features. That's the whole point. And then we are actually going to use a training set. A testing set. So once we train our model the first time, we're going to test it. And this is data that the algorithm has never seen before. The model's never seen it before. And we're going to use this to test and see if our model is accurate enough or has a high enough recall or a high enough recall or a high enough. Oh, I've lost the word in English now. Somebody used it in a bit, not accuracy, but precision and recall. So depending on what we want to use, we're going to do it in our testing set. Again, data that our model has never seen before. Now, this becomes really, really, really important because we want to mitigate something that tends to happen if we don't, which is called overfitting. All right. Oh, Jennifer, that's a great question. How do we choose what to use as the training set? So again, we're going to use our data as the training set. Now, when you split training and testing, you don't choose. You do it randomly. If you choose, you're doing a disservice to yourself because then the model, you're sort of going to cheat and make the model work better, but it's going to, when you test it, it's not going to work as well. So you actually, all of these splits, you do them automatically, randomly. So there's actually a lot of functions. For example, in scikit-learn, there's train test split, and you just tell it if you want 80% or 70% in training and the rest in testing. And it does it automatically. So it takes, imagine that you have 1,000,000 rows of data. It's going to take 700,000 rows, and it's going to transform that into the training set. And it's going to take 300,000 rows, and that's going to be your testing set. So what we're trying to do, yes, Python will do that for you. What we're trying to do is avoid overfitting. So imagine that you had just two variables, and you're trying to predict one on the other, and they look like this on a scatter plot. All right? They look like this. So it turns out that because you don't have that many points, and it looks like it's a little bit linear, you want to build some kind of a linear model. So if you overfit it, this is what it's going to do. It's going to learn the points, and it's going to do this. It's going to go here, and then to the other point, and then up to the other point, and then this, and then this. And I think these 2 points shouldn't be there. I'm going to remove them. So it's going to look something like this. That's overfitting. In other words, this is a line that's great for predicting the values it has already seen. But if we give it a new point, which is here, now it's not as useful. If it's another point here, then it's not as useful either. So with new data, if you overfit, it's just not going to work. On the other hand, you don't want it to underfit either. So that's the challenge. So imagine you have a training set like this. So a perfect fit would be something like this. So it's not perfect. It's not going to be 100% accurate, but it's good enough. But if you underfit, it's going to look like this. So again, it's going to work really well on these, but it's going to work really badly on points that are farther along. So that's the whole point. We don't want to overfit, and we definitely don't want to underfit. How do we know you need to split? This one's an easy question. You always need to split. Why? Because you always want to be able to test your model in data that it's never seen before. There are much more advanced techniques where you can actually train and test your data and then switch the test and training set and train again and things like that. But initially, you always want to split your data set. By the way, and this I'll leave to you as an idea to research before we go on a break. What happens if you're trying to, for example, let's say you want to build a system that can recognize dogs in dog pictures, but only 5% of your pictures are dog pictures and the rest are something else. What would you do in that case? So I'll leave you with that question. and we'll take our 10-minute break, go grab a drink, go grab a snack, go stretch your legs, and we'll continue with feature engineering in 10 minutes. All right, everyone. So we're getting back. Let me share my screen again, the right one. Okay, so yeah, we're back. So we were talking about the life cycle of machine learning. We just did this data splitting, and now we're talking about feature engineering. So feature engineering has to do with picking those right or the best features from our data set to run our model. Now, features are everything inside our data. So to give an example, and this is a classic example of a machine learning problem, there's a data set called the iris data set. So it has 3 different kinds of iris flowers. And what we have is the information on several features. So for example, we have color, petal length, petal width, sepal length. The sepal is like the little leafy thing right underneath the petal. Can you hear me okay? Or is it too low? Give me just a second. That seems to be me. It happens. Can you hear me now? Better? Better? Okay. Wonderful. So if we wanted to build a machine learning model with all of these data, which features of the irises would we pick? So as I mentioned, we want to pick the ones that are going to help us predict, for example, from the data, from petal length, petal width, color, we can predict what kind of iris it is. So if that's what we're trying to do, then we want to figure out which of these features, color, petal length, width, sepal width, etc., are the ones that are the better predictors. Now, if the data set is not too big, in a sense that we have enough computing power to run the whole thing, we probably want to use all of the features that we have. But there do come some cases where we have too many features. And the problem that I want you to think about is, imagine that you have, so let's say that we have a data set that has 1,000 rows and 10 columns. So imagine that for every column and for every feature that we use, so for every column and every row, we need to process 10 pieces of information. All right. So how many pieces of information would we need to process when we run this data set? That's 10 columns and 1,000 rows. Any idea? 10,000. Yes. So it's 1,000. Sorry, 10 times 1,000. Now, I want you to imagine this. What happened if instead of 10 rows, we had 100 rows? Then how many pieces of information do we need to process now? Yeah, it just went up by 10, but a factor of 10. So now it's 100 times 1,000. Oops. And again, most of our data sets are not 1,000 rows. They're many, many, many more. So the more columns we have, so every time we add a column, we need to multiply by the number of rows we have. So now imagine we have 10 million rows. So every column we use, we have to multiply by 1 million. So that's a lot of processing power. So we need to figure out, if we don't have enough process power, which of the features we need to cut out. That's why feature selection becomes so important. Not only that, but there might be some features that are so unrelated to our target variable that they're just noise, and we actually want to remove the noise. So that's the thing. So imagine that from the photos or from our irises, we pick the ones that have the highest correlation to the type, and those are the ones we're going to use. So it becomes important, and the rest of them we just remove them from our data set, from the data set that we're going to be using for training. So again, what we want to do with machine learning is to develop a model. Now, the important things that we need to figure out is, for example, in this case, see that we have color. So color is not a number. Color is a quality. Red, blue, yellow. Those are things that computers don't understand. So one of the most important things that we need to do when we do our feature engineering is we need to transform our categorical columns into numerical columns. No, it's not even a matter of a string. It's a matter of that, again, a computer does not understand yellow. So we need to figure out what that means. So most of the time, what we do is we just change it into some kind of numbers. So for example, if we have genders, male and female, so we encode them and we just transform male and female. So one of them becomes a 1 and the other one becomes a 0. It becomes a Boolean variable. So because they're either male or female in this case. Or we do, for example, do they smoke? Which is something that happens. Are they a smoker? So 0 means no, and 1 means yes. But we need to encode these into our systems, or the system will not work. No, generally we don't use hex code because that's adding another set of problems. It's not only unstructured data, we're just trying to let the computer understand what our data actually means. Here's another interesting example. Let's say that you have what's this one? Let's say that, for example, what happens if you have color, or if you have, this is an interesting one. What happens if you have, for example, color? Let's say that you have 3 possible colors. You have white, or you have yellow, you have green, and you have blue. How would you encode them? Because there's tons of ways, and there are better ways to encode them. So generally, if you only have 3 different colors, you can generally just do exactly. We can do 0, 1, and 2. But here's a problem with doing this. And actually, when we're doing male and female, that's also a problem. So, and the problem is that, here's a question. Do these numbers mean something to the computer? So it turns out it does. Why? Because 1 is bigger than 0, and 2 is bigger than 1, and 2 is definitely bigger than 0. So these numbers have certain order. And because they have certain order, the computer might actually, the algorithm might actually look at them and figure that a 2 is more important than a 1, so it should have more weight. And that can be a problem. So there's a cool thing that we tend to do when we have these kinds of variables, which is called one-hot encoding. So instead of plugging in just 0, 1, 2, we actually plug in arrays. So in this case, this will be 1, 0, 0 for yellow. Then we have an array for green, which would be 0, 1, 0. And then we have one for blue, which is 0, 0, 1. Now, in this case, they all weigh the same. They all have a weight of 1. So it doesn't matter. So what we do in this case, we're just encoding these features that are categorical into features that are numerical. But in this case, they're numerical, but they don't weigh one more than the other. They're not ordinal. They don't have any order, which becomes interesting. So, yeah, sometimes math can feel like philosophy, but it's not. What we're trying to do is we're trying to use mathematics to describe things that are not mathematical in nature. Like shapes. We can actually describe shapes in math. But the thing is, you have to stop thinking in a sense of the mathematics, 1 + 1, 1 + 2, 10 times 20. So, and you still have to start thinking in mathematics as a way to tell a computer how the world is shaped. That's one of the things we do with that one-hot encoding. So great. Once we figure out what the features are, then we do the predictive modeling. So depending on what we're doing, we pick whatever algorithm is going to work best or whatever target we have. And we let the algorithm actually find the patterns that we want to have. So again, depending on the type of data, the desired output, and the specific application, that's the specific machine learning technique that we're going to use. Technique and the algorithm. So for example, there's two main categories. The first one's called supervised learning. So in supervised learning, we actually want to build something, we're giving it all the information, and there is a correct answer. So, let's say, what's the price of this house? So we have all these features, 10 bathrooms, 2 bedrooms, 1,000 square meters. And the price is $1 million. Okay. And we have, tons of data like that. So that's what we call labeled. So labeled means that we have the target variable. See the price, we give it to the system. So the system can figure out what the relationship is. And that's great to predict or classify outcomes based on labeled data. So for example, is it a dog or a cat? We give it a lot of pictures of dogs, pictures of cats. This one's a dog, this was not a dog. Figure it out. This is called a guided method because it's going to learn how to map all of the features to the target variable. The applications, there's tons of applications, regression, classification, support vector machines, etc. And so examples, what do we use this for? We can use it for weather forecasting, for image classification, for spam filtering, tons of uses. And then we have unsupervised learning. So in unsupervised learning, we just have data. We don't have a target variable. So this changes. So I want you to think about we don't want to figure out, how much a client is going to purchase from us, but we want to see if we can group customers into different segments. And then we try to figure out what those segments mean. So that's a great problem for unsupervised learning. So in this case, we have unlabeled data. There's no known outcomes because we're not looking for an outcome. And we use these to actually find patterns in unlabeled data. So we give it a lot of pictures and we say, group them into 3 groups because of how they look. And it turns out it's actually really good at grouping things together. These look like dog-like, these look cat-like, for example. This one's unguided. So it's going to learn to identify patterns by grouping them together, by figuring out which ones belong with which other. So the applications, we used it for clustering, like, grouping groups of clients, something called anomaly detection. So for example, if somebody uses your credit or debit card and they shouldn't, or because they stole your numbers, we can actually use unsupervised learning to figure out which are those anomalies that actually happen, which become or could be fraudulent activity. As some examples called customer segmentation, like we just talked about. And the other one, which I love, is market basket analysis. So which products do people tend to purchase together? Market basket analysis, by the way, is also how you get recommendations from Netflix. A ton of people who have watched stuff that you've watched have also watched this. So that's what they show you. And Amazon, yes. So that's called, so market basket analysis, anything that has to do with shopping at a supermarket, they use market basket analysis. Great. And finally, we do data visualization. So we already did some data visualization in EDA or exploratory data analysis. But now we actually put it because we want to compare how the model is performing, how each model, because we don't generally build only one, we build more than one. And we might build different versions, and then we figure out how it's actually working. So we actually create charts, graphs, and we actually build dashboards in Tableau, Power BI, Looker Studio, etc. And this is how we present our findings. And this is how we can present, hey, look, we built this model. This model got us to a certain level of accuracy. We think is good enough. We can actually deploy it. Hey, it's not good enough yet. We need these other things to actually try and make it better, to see if it's going to work before we can deploy it. Because again, one of the things that we need to think about, more than right now, I would say about 80 to 85% of machine learning projects never end up in a functional model. But that's not bad. That's just how it is, because then you have to keep looking for more data, different approaches until you actually find what you're looking for. All right, questions so far? Before we get into supervised and unsupervised learning. All right. Okay, so a little bit about, let's talk a bit more about supervised learning or supervised machine learning. So again, this is something where we actually want to make specific predictions about something that we've never seen before, or something that should be the future based on past data. That's the whole idea of supervised learning. So the big thing that distinguishes supervised machine learning from any other machine learning model is the labels. So all of the data that we input is labeled, meaning that whatever variable we want to predict is in our original data. We're not making anything else up. We're not trying to cluster people together. We just want to figure out, for example, the price of a product, the price of a stock, whether the email is spam or not, whether a client will pay us back or not, if we lend them money, all of those specific things. That's what we're looking for in new scenarios. So again, think about what we're talking about. We want to build a model that can actually predict whether the picture is a dog or a cat. So we're going to feed it a lot of images, thousands, hundreds of thousands, millions of images, or dogs and not dogs. The important thing is this little label. See here, this one's a dog, this one's a dog, this one's not a dog, not a dog, and not a dog. So we feed all of them into the supervised learning model. And at the end, we are supposed to, we build a machine learning model that is able, once we put a new picture in it, to say, hey, look, this is the new picture you've never seen before. Hey, this is not a dog, because it does not look or the pixels do not line up the way the dog pixels line up. Somebody mentioned in a bit that this is kind of a black box. You just put something in it and you get something out. It can be, but there are a lot of methods which can get a little bit more complex to actually get into this box and figure out why or how the system is figuring out how this is a dog and how this is a cat. So to build a supervised machine learning model is actually divided into two separate parts. So the first part is the training and testing process. So this actually leads to a model to be evaluated. And this is very, very important so that we can move into the inference process. So again, what we do is we input the data set. Remember, we got all the way to feature engineering, and this is what happens in the actual building the model. We input the data set, we curate it, before we got the data set, we curated it or cleaned it, we split it, we did the data engineering, and then we go into the training phase. So we train it, and that creates our machine learning model. We train it using an algorithm that creates our model, and then we test it, all right? Once we test it, once we run this several times and we have an accuracy, precision, or recall that we want, then we move it into the prediction test, and then we take new data, we feed it new data, and we look at the label outcome. So if this is working at a high enough percentage or well enough, we can actually deploy this to production, where we're actually going to use it to automate all kinds of decision making. So one interesting example, I don't know if you've heard about an insurance company called Lemonade, like the drink. So Lemonade actually uses machine learning. You can actually do a claim with their app. They run it through their machine learning model, and it tells you whether it gets approved or not. If it doesn't get approved, you're not done. It just moves to a human person. But about 90% of their claims actually get approved through the machine learning model, which is really cool, by the way. So again, what we do is we input the data set in supervised learning, everything with the features and the models. So remember our iris dataset, we have the sepal length, the sepal width, the petal length, petal width, and the class. So again, we are inputting everything. This is our target variable right here. Oops. This is our target variable. This is the name of the iris. This is what we want. All right. So once we do that, so we have it has all the features and all of the labels. Then we do the data curation. So we make sure that everything's clean, that there's no null values, that we have everything. That, for example, remember the example that I mentioned earlier? If you're doing spam, not spam, but you only have, I don't know, maybe 5% of your emails are spam, then you actually have to either get rid of a lot of the non-spam emails, or you actually have to figure out how to augment the number of spam emails. There are techniques for that, because you want both classes to be about the same. They don't have to be the same, but to be about 40, 60, 50, close to 50-50 if you can. Then we do the data splitting, of course. So for example, we do it by 70-30 rule, or we do 80-20, depending on the size of our data set. We do the feature engineering. We figure out what things to keep and what things to get rid of. We transform whatever features we need to transform. And finally, we fit it. So fitting the model means we give it all the data, let it run. It goes through several epochs most of the time. It keeps getting better up to a certain point, and once it reaches peak performance, we stop, because we know it's not going to get any better, or it starts getting worse, actually. So once it reaches the top performance that it can, it could be 80%, 85%, 90%, depending on where we want to get, we actually stop it. Once we stop it, we test it to see how it works, not just on the training data, but on the testing set. And if it works well on the testing set, then we have a model that actually works. And again, here we're trying to avoid overfitting. So again, if a model is overfitting, it's going to perform really well on the training data set, and it tends to perform quite a lot poorer on the testing set. By the way, it's usual to perform a little bit less than, so training should be up here, testing could be down a little bit lower. That's normal. But if it's very much lower, it's probably overfitting. On the other hand, we also want to avoid underfitting. So again, with underfitting, what's happening is that it performs badly on the training set and even worse on the testing set. Yes, so there's a lot of ways to avoid overfitting, but it still can happen. The thing is that one of the reasons we test is to avoid overfitting, because we can actually figure out if it's, so for example, if you get 95% on the training set and you get 60% on the testing set, you know it's probably overfitting somewhere. And then you can switch some things around and then do again. There's techniques for everything, for overfitting, for underfitting, for refining, for improving, etc. And remember, one of the things that we tend to do, by the way, and this is just, we tend to start with simple models. So one of the things that a lot of people want to do is, for example, dive in to doing something like deep learning. So deep learning is much more complex and it requires much more compute power. So sometimes you start with something simple, even a linear regression model, a simple decision tree model. Why? Because if those sort of work, then you know you can improve them using much more robust models, like deep learning, for example. But first, you want to prove to see if you're going somewhere with the much more simple models. And some of these simple models, like linear regression, they have a ton of tiny tweaks and tiny things you can do to actually improve them. So that's actually interesting. So sometimes types of supervised machine learning models, the most common one is the regression. So again, these are great for numerical when we're trying to, or target variable is numerical, especially when it's continuous, but when it's numerical, they work really well. So for example, sales forecasting and house price predicting. So again, in these kind of systems, we can actually fit a line, and that line tends to be really good. Again, lines don't necessarily mean that they have to be straight. They can be curved, and they can have several curves, polynomial. But this is a great model, and it's always a great starter model. I always start with some kind of a linear regression model. And then we also have classification models. So for example, support vector machines, logistic regression, another kind of regression, but instead of just trying to put something on a line, it's actually saying where it falls regarding the line. If it falls on one side, it's one category. If it falls on another side, it's the other category. So for example, for spam filtering, interestingly, for image recognition, so because it actually, this is a great model for classifying or categorizing objects, faces, etc. And we also use classification for sentiment analysis. So for example, are people happy with our product? Are they talking positively about our product or negatively on social media? Great, that's supervised learning. Actually, no, CAPTCHAs are quite much more mundane, believe it or not. So CAPTCHAs are just something that supposedly machines should not be able to do. But machines are becoming more capable. But so that's a different problem. Proving you're not a robot is a different problem. So unsupervised machine learning. So we talked about supervised. What about unsupervised, the one that doesn't require supervision? Because we don't give it the answer. We don't give it the labels. So we use it to uncover patterns. We want to look for patterns, unlock relationships that we haven't seen before, that we don't understand, we don't know they exist. So again, we don't require pre-labeled data because we're not looking for a target variable in this case. So again, it uses unlabeled data. So again, data that don't have any predefined labels or categories. So the algorithms, all they do is try to group things together by trying to match them to see how close they are between each other. Then we have pattern discovery. That's what we want to do. We want to discover patterns. So for example, if we're clustering clients, well, it might say, well, these are the clients that live in a certain area and spend a lot of money. This live in a different area and spend money, things like that. So it's going to look at all the variables and try to cluster them together. And there's no predetermined output. So again, because we're not looking to specify outcomes, all we can do is say, split this data into 3 groups, 4 groups, 5 groups, and then you figure out which one works better. There's ways to figure out which splitting makes more sense, by the way, which are much other mathematical algorithms. So factor analysis or PCA, principal component analysis, which is really interesting. So things that we use it for: customer segmentation. We want to cluster customers by preferences, by spending, by behavior, etc. Fraud detection. So we try to identify anomalous transactions in credit cards, debit cards, bank wires to see this is wrong, this is happening. Recommender systems. So to recommend you something like the Amazon website or a Netflix movie. We use, again, this is unsupervised learning. Image analysis. Again, image analysis, not recognition. We're not trying to recognize or figure out what this is. We're trying to group it by similarity. And we also use it for text mining. So for example, discovering specific topics. So let's say, what are people writing about in a certain area? We use text mining, and it turns out that, I don't know, 30% of the people are writing about artificial intelligence because it's the cool subject. Some common types of unsupervised machine learning models. So we have clustering, like k-means clustering or KNN, K nearest neighbors. Again, we want to group things by similarity. And what it uses is mathematical similarity between one and the other to see where it should go using, when it says k-means, it's looking for centroids, how many groups you want. It tries to look for the center of those groups and then organize everything around those. Dimensionality reduction, or PCA, principal component analysis. I'm going to use a bad mathematical word. It uses a principle called orthogonality to figure out which are the most important factors and which factors we can just join together. So think about it like this. What we're trying to do with PCA is to reduce the number of components or features we're going to use inside another machine learning model, but not losing any of the data. Or at least that's the principle of PCA. Anomaly detection. Again, something like local outlier factor. So whenever you see, you start grouping all of the transactions together. Think about, for example, credit card transactions, and suddenly there's dots that just don't conform to any of the groups. That's called local outlier. It's looking for outliers inside the local groups to see if something's happening. Yes, Ben, by the way, yes, I actually use PCA all the time so that we can actually get some psychometrics with like high-end psychometrics with 60 items instead of 720, because nobody wants to answer 720 items. But 60, it actually takes about 5 minutes. And association rule learning, like a priori algorithm, which is great. This is for example, we use for basket analysis. So what it does is to discover frequent item sets in a data set. So for example, if you have watched these 20 movies and I have watched these 20 movies and you've watched 2 more and I haven't, it's going to say, hey, you should look at these 2. Or if generally we see that bread and butter are purchased together. So, hey, look, these 2 items, so we should put the bread close to the butter or the butter close to the bread, which, by the way, is the kind of things that supermarkets do. So whenever you see something weird hanging in a supermarket in an area that does not belong, there's an algorithm that told them that for whatever reason, that belongs there. So for example, you suddenly see Reese's Pieces right beside the carbon and barbecue things. Well, maybe people are actually eating Reese's during barbecues. For some reason. All right. So which of these, let's do a little bit of a question. Which of these is not a common technique used in unsupervised learning? Clustering, association, rule mining, or decision trees? So yeah, it's definitely decision trees. And by the way, decision trees are one of my favorite algorithms, specifically a more advanced version called XGBoost. So XGBoost is there's decision trees, then you have random forests, which are a bunch of decision trees working together, and then you have XGBoost, which is a bunch of trees working together and being pruned at the same time, so that they're shorter and they actually think faster. So it's really, really interesting techniques that can get really powerful. And which of these is not a common application of supervised learning? Market basket analysis, spam filtering, or medical diagnosis? Yep. So market basket analysis is an unsupervised learning technique, not supervised. All right. Finally, for today, we have a little bit of, we're going to talk a little bit about generative artificial intelligence, or Gen AI. So, by the way, has anybody heard about the term artificial general intelligence, AGI? So AGI is the objective of artificial intelligence. Artificial general intelligence means an AI system that is smart enough to learn by itself, to do other things. So one of the biggest things that I can tell you is none of the systems that we have today can learn to do something else except what they've been taught to do. So for example, even if LLMs look like they're actually talking to you and that they have a personality, they're just imitating things. You cannot teach an LLM, for example, to cook you something, because it can't interact to the world. And even if it could, even if it was we put into a robot that could cook, it probably can learn to cook, because there's many other things happen. If we could, autonomous cars would be much smarter than they are today, which they're not. So that's AGI. We're not close to AGI yet. No matter what people say so far, we're not even close to artificial general intelligence. We're very, very far from it. But we do have really interesting things that can actually analyze, interpret data, create new content like LLMs do. We can create images, we can create audio, we can create code. And it's actually learning how to create video, which is really, really interesting. Now, for me, the most powerful thing about LLMs is that it's giving us a new way to interact with computer systems. No longer, it's not just limited to code anymore. We can actually interact with computer systems through LLM systems. But we're still a long way from AGI. And for example, Star Trek, computer, do this, and then the computer does it for you. If you have an Alexa system or something like that, so half of the time you say, Alexa, do this, and it does something completely different. So yeah, we're still working on it. It's going to take a while. So remember, we talked about the hierarchical relationship earlier. So we have artificial intelligence up top. Inside artificial intelligence, we have machine learning, which is a type of AI. Inside ML, we have deep learning. And because generative AI systems were built using deep learning, they are inside of deep learning. So everything is in deep learning. Of course, as I mentioned, there's other things happening here at the same time, like natural language processing. So for generative AI, by the way, deep learning is vital. Without deep learning, we can't do generative AI. And it requires several DL techniques, not just the normal one. The first one is called neural networks. This is the most basic deep learning system. So as I mentioned, deep learning systems work something like this. So you have all of the features. So actually, let's say you have the features over here. Sorry, my drawings are not the best. And then you have several layers of what's called perceptrons. So perceptrons try to work out like neurons. And what happens is that all of the information gets fed to every single one of the perceptrons as the layers go in. That's why they become really complex. And here's where feature engineering becomes even more important. Because now, for every single piece of information, oops, I'm missing this. As you can see, even in my very, very rustic drawing, things are getting really complicated really fast. And then this, again, connects to every single one of them and so on, until you end up with whatever output neuron you want, depending on what you're trying to do. And each of these is running weights, and each of these is running statistical algorithms. So it becomes really complicated really quickly. But it doesn't stop there. This actually makes it really, really powerful to figure out patterns, because it starts adjusting the weights every time it goes back and forth. It adjusts the weights, and it adjusts whatever calculation it's done in every perceptron until it can actually figure out the pattern the best possible way. So now that leads us to something called generative adversarial networks. So with these, we actually had one neural network creating something. So it created A. And then we had a second network look at A and criticize it. So it's like building a critic. That's why it's called adversarial. So imagine that this is the critic. It's telling you, hey, no, this looks nothing like the original. You're really bad at this. You shouldn't do this. You made a mistake with this, with this, with this, and with this. So that information goes back into the original one. And then now it does a better A. And then this one criticizes it again, and so on, and so on, and so on, until it comes out with something that's really interesting. Yeah, well, so the idea, it's sort of kind of how the brain works, or how it works in a very, very simple term, because the brain is still much more complex than that, especially because even the most complex neural network does not have as many neurons as you have in your head. So still, it's a matter of how many. So we cannot process information as fast as computers, but we can process a lot more information in a lot of different ways that computers cannot, at least not at this point in time. Then we use something called variational autoencoders. That these are sort of the Latin representation of the input data and the generated examples. So just to give you an idea, whenever you're working with an LLM, this is what happens. You write something, so this is your text. Now this goes into an LLM, into one part of the LLM. It gets transformed into something called encodings, which are just numbers. So imagine these are just numbers. Those encodings get fed into the other part of the LLM, which that's its magic with statistical methods and all the like. And this outputs another set of encodings, which is the response. These encodings go into the first part of the LLM and get transformed into words again, and you get your response. But at the end of the day, everything's math. For these systems, everything is mathematics. Mostly statistics and probability, by the way. And finally, we have transformer models. So LLMs are actually built on what's called the transformer architecture. And they're very cool. And it would take me probably about 2 whole hours to explain you how a transformer works. It's not like like Optimus Prime, but they're very cool. So if you're interested in them, I would actually suggest you look into them. If you're really interested in how LLMs work, transformer models are brilliant, but you actually have to go through neural networks, generative GANs, variational encoders to then understand how these models actually work. By the way, if you are interested, I would suggest looking at videos from Andrew Ng. I'm actually going to write it on the chat. Andrew, it's not here. It's here. Andrew Ng. And if you can find any one of his videos of courses on how neural networks work, it's brilliant. And by the way, I'm a big fan of what he says every time. Don't worry about the math. Just try to understand the intuition behind it. Really don't worry about the math. So what are some of the real world applications of generative AI today? Well, first of all, content creation. So this is what it's being used for the most. Now we're generating articles, scripts, books, code, art, and music. So all kinds of things we can do. There's tons of things to talk about yet about intellectual property, about copying other artists, tons of things and tons of issues that we're still discussing, probably a little bit slower than we should, but it's important. Then we have drug discovery. So drug discovery, this has been one major advantage of generative AI because it's actually helped develop new drugs and new molecules that we didn't think were possible. Or it would have taken us a lot of time to figure those out. Of course, customer service, now we have chatbots, we have systems. I would probably say that the biggest systems right now are the ones that offer you personalized ads. So if you do not want those personalized ads, just opt out of everything. Entertainment, of course. Now it's creating new things for entertainment. There's tons of bots out there just creating things. Some of them for entertainment value, some of them not so much, but that's a different thing. And finally, design. It's being used for designing new things, automating the design process. It can be used for architecture and things like that. Now, the potential is vast, and the impact that it's having on society is very big and very profound. It's going to get more innovative. It's going to get bigger. It's going to get more interesting. And there's definitely a ton of things that we need to talk about regarding generative AI. But it is probably a transformative technology, just like the internet was at one point in time. There's a growing concern that AI might eventually replace human jobs. In your opinion, is there a chance that the role of data analysts, which we're currently studying for, could be taken over by AI in the future? That's a great question. So first of all, a job replacement, it's not the first technology that's replacing jobs. And what tends to happen is it starts creating other jobs. Second, will it eventually replace data analysts? I mean, I ask myself this because people are talking about replacing programmers and replacing this. Truth be told, it might replace the lowest level of people. People who are just doing specific chores that can be automated in some cases. But the higher end of thinking and producing is probably not. And this is something that happens over and over again. So it just creates new opportunities and options. I'll give you an example. So everybody's been talking about vibe coding. So, tell the LLM what you want and it's going to code it for you. Well, it turns out that people who have been doing this, so if you're programming and you're vibe coding, what tends to happen is if you're trying to do everything at the same time, if you used to spend 20 hours coding something, now you're spending 30 minutes telling the LLM what to do and about 40 hours fixing it. So it's not working as expected. Now it is working for very simple things, but once we get to the more complex things, it requires humans. And that's one of the things that tends to happen with technology. So technology starts replacing the lower level jobs, but it creates a lot of new jobs up top. And why it does that is because once you cover this launches new opportunities. So if you're an okay coder, you can actually use LLMs to be a much better coder. All right. So now you don't need to get to, but if you don't know anything about coding, odds are you can't, you're going to try and code something with an LLM and it's going to be messy, very messy, and you're not going to get it to work the way you want it. And the same thing happens, and this is something that has happened over and over again. Now, are there dangers that a lot of jobs are going to disappear? Yes, definitely. Especially jobs that for the longest time we thought it was going to be just never replaceable by machines. But the important thing is that you build a base, because right now I would say that I could divide the world in two people who understand technology and can actually build things with technology, and people who can't. And unfortunately, the people who can't, they are the ones that get dragged behind farther and farther, depending on what career they're on, versus the people who understand technology enough to build things with it. Those are the ones that can still look for ways to be relevant. But that's just my take on it. We don't have enough data yet. That's the other problem. We do not have enough data, and it's all speculation. Because some of these technologies are so can lead to so many changes. There is no way, and we don't have systems that could capture enough data. We don't have enough data, and we couldn't even have a system that can manage the amount of data to figure out what's next in the world. It's a lot of data. I'm going to remember a series that actually talks about this problem, and I'll post it, but I don't remember the name of it right now. I saw it quite a couple of years, 2 or 3 years ago. All right. So all we got today, so we got through a little bit of a foundational overview of data science. My suggestion is, if you like data science, practice coding quite a bit more, practice your SQL skills, start looking into what machine learning is, how you can exploit the power of machine learning using Python, go into Kaggle, do things in Kaggle, and keep learning. So again, as I said, I'm probably the one person that has practiced this idea of keep learning your whole life, never stop learning. And if technology is interesting to you and data science is interesting to you, go into it, keep learning. And even data analytics is going to keep changing. There's going to be new things, there's going to be new tools, and the more you learn, the better prepared you're going to be to not just to have a job, but to do something amazing in the future. Questions? Feel free to ask about anything. This is a good time about it. We have about 7 or 8 minutes left. AGI system that dooms Skynet or HAL 9000. Interesting. I'm actually more afraid of Viki. If you don't know Viki, I suggest. So if you're afraid about the future, my biggest suggestion is read a lot of science fiction. I've always thought that science fiction authors are great at looking at what might happen. Because, for example, do you know who the first person to ever talk about a microwave was? Jules Verne, 20,000 Leagues Under the Sea. Captain Nemo in his submarine, he has a microwave. And nobody even knew what that could even be. So it turns out, think about Star Trek. We have iPads now. Remember that they were carrying iPads here and there all over the place? We have them now. So yeah, read a lot of science fiction. By the way, Vicky is from I, Robot by Isaac Asimov. Great book. Movie, okay movie. Isamar, no, actually, you don't necessarily need to major in something and then get into data science, because you can always learn whatever interests you. Once you know data science or data analytics, you can get into almost any industry and learn from there. Generally, junior data analytics roles do not require a lot of industry knowledge, and you can get it while on the job, and it keeps you open. So, for example, I never thought about learning data science when I was studying psychology. If I did, I would have done it the other way around. I should have. Data science was not a thing back then, but details. The thing is that you can always learn about the industry as you work, or because it's just interesting to you. But so no, I mean, get good at the tools of the trade. I mean, the tools are going to, so for example, if you know how to code, a lot of things open up in your life. If you know SQL, a bunch of other things open up. And if you start putting them together, then you have you start getting limitless options. So Rob, that's a great question. Do I have a portfolio that I keep around? I do have a portfolio. I do not make it public. That's me, because I already am working with a company that I help found. So, things work a little bit differently, but I do have a portfolio that if tomorrow I needed to go look for a job, I would just post it up there very, very quickly. To train learning models, Kaggle. So going to Kaggle has a lot of resources to teach you how to build models. And there's a lot of people in Kaggle and a lot of notebooks there that can actually help you and walk you through building models. So for learning machine learning and deep learning. So yeah, anything from Andrew Ng is a great idea. I would also, again, going to Kaggle, I know Kanji is not doing a lot of content anymore. I have to look to see, because I haven't been paying attention about who's creating a lot of new of content about the basics of machine learning, but I would suggest you start with Kaggle. That would probably be the best place. They have courses, and they have a lot of notebooks there. And I'll look for a few things, and I'll let you know on the extra help channel. Yes, the movie I, Robot. Yeah, I don't know if it completely missed the point of the book, but yeah, it was compared to the book. But that usually happens. It's very unusual that the movie is better than the book. Wow. What kinds of businesses do you think can effectively leverage data science to generate revenue? Well, here's the thing. I think most of them could, but I think the biggest value of data science is not necessarily in generating revenue. There's maybe a lot of power in creating other types of shortcuts and predictions inside the company that are going to help them improve processes, make things faster, make things cost less, and all of those things are going to lead to better revenue. So just to give you an example, additive manufacturing, which is the correct name for 3D printing, it turns out that they're using machine learning models to figure out, for example, how to create a steel frame that requires the least amount of steel possible. So again, that in itself is not generating revenue, but it is cutting costs. So again, don't focus necessarily on generating revenue, but on creating value. And think about what value might be for value can change for different companies. But other examples of generating revenue using machine learning, well, improving customer relations is always a good one. Improving the speed with which you deliver updates for computer companies. There were new models, for example, new machine learning models of how to deliver things for logistic companies. So, for example, improve routing, how to improve routes, how to improve shipping, all kinds of things. And again, what it's going to do is generate value, which not necessarily transforms to revenue, but at some point it sort of does. Will AI and machines replace adults in raising children? I don't know. I mean, are we in the matrix right now? I really don't know. So that's a great question. Yes, LinkedIn is probably the best place to connect. My LinkedIn is on the network channel, just in case. For machine learning, Python. Python. So even though they've even tried to move some machine learning into JavaScript, Python. Yeah, do get more skills. So, but you can be at least for the foreseeable future. Most coding for machine learning and data science will be done on Python. It's just getting bigger instead of smaller. So. No, Wendy, no, not that Vicky, not Vicky from. I remember, I remember that show, but I don't remember the name. But yeah, that's another Vicky. How do you determine that you're proficient enough in a programming language? That's a great question. What have you built? That would be my question. What can you build with it? So, for example, if you to be and what do you want to do with it? If you want to build games and you're able to build a game, it doesn't matter if it's simple, then yes, you're proficient enough. If you want to build machine learning models, like deep learning models, and you're able to actually build one, you're proficient enough. So yeah, that's a difficult question to answer because it really depends on what you want to do. So for example, a video game programmer will probably never see a machine learning library. The same way that if you're into machine learning, you might know all the libraries like scikit-learn and PyTorch and TensorFlow, but you will never even open Pygames, which is for gaming. So, no, R can do a lot of machine learning. R is a very, very powerful library. I actually like R a lot. My only issue with R is that when it's time to take that model and put into production, there's loads of challenges you do not have with Python because people are just not used to working with R as much as they are working with Python. But I love R. I mean, R is an amazing language for everything that has to do with data, especially, tidyverse for exploratory data analysis. I'll take that any day. But unfortunately, Python, ML is ruled with Python. All right. So if you have any more questions, feel free to post them. I'll try to get to them.